This episode is dedicated to my sister, who made this YouTube channel possible. Okay, now, without further ado, let's dive into today's episode. Today, we are going to take a look at our favorite star system in the universe, of which we know the most of, and like to study and explore. Today, we are going to take a look at our cosmic home and how it got started. Today, we are going to take a look at the beginning of the solar system. Starting from the beginning, at 4.7 billion years ago, in an interstellar molecular cloud that was made mostly out of hydrogen, helium, and a bunch of other compounds like water, methane, and organic molecules, and which was 65 light years across, due to gravity, started to fragment into 200 to 400 more smaller molecular clouds, with each having between 2000 and a 20,000 astronomical unit wide diameter, that were called protostellar nebulas. In one of these nebulas, our Sun started to form, as a shockwave from a nearby supernova has nudged these clouds, giving them angular momentum, and kick-starting a process of cosmic star formation that eventually resulted in us having this conversation today. But these sister stars that formed along our Sun from the same cosmic cloud haven't managed to retain their initial position in space, migrating over time across the vastness of space due to the gravitational influence of nearby stars and even of the galaxy itself, moving away from one another and eventually ending up in different positions around the galactic core. After the Sun's cosmic cloud got its angular momentum from the supernova explosion, now being called the pre-solar nebula, it started to rotate, pulling content and matter into a vortex-like structure that over several thousand years arranged this pre-solar nebula into a disc-like shape where it was uninterruptedly feeding gas to the newly forming Sun. For around 100,000 years, the gas orbiting the disk accelerated as it approached the center, compressing matter around this embryo of our Sun until a stable sphere of hot gas was formed. And after this point, the gas in our nebula had managed to flatten into a 200 astronomical unit wide disk, being left with only 20% of the initial mass of the protostellar nebula. As time passed by, the Sun started slowly to ignite, as it further compressed a lot of hot swirling gas around it, further increasing its mass whilst ejecting twin flowing jets of gas along the way. As matter was consumed, the envelope around the Sun slowly began to disappear, making the Sun visible, at first in the infrared and over time in the visible spectrum. Fusing deuterium in the beginning, as it took the shape of a brown dwarf after reaching 13 Jupiter masses, but after it managed to surpass the threshold of 80 Jupiter masses, it started for the first time in its life to fuse hydrogen, starting to generate enough outward pressure as it began to erupt jets from the photosphere that over 1 million years managed to clear all of the envelope from around the Sun. At this moment in time, the Sun was now a T Tauri star, a young star, where the material from the accretion disk has not yet turned into planets, hitting its surface at the poles and generating a variety of spectral emissions, magnetic activity, and twin polar jets. This stage of its life lasted for 10 million years, until the accretion disk, now protoplanetary disk, had cleared, with planets not being able to form in the star system after this point in time. So, what happened in this 10 million year span of time in the solar system's past? What dynamics were present at that moment in time that led to our present configuration of planets, moons, and asteroids? Let's find out, shall we? So, in the first part of the T Tauri stage, the protoplanetary disk was way too hot for things to form, having around 400 degrees Kelvin up to 4 astronomical units away from the Sun, and 1000 degrees Kelvin within 1 astronomical unit distance, vaporizing all the volatile substances like the methane and the water in this area of space and ejecting them to the outer disk of this system. But as time passed by, and the temperatures were able to drop as the disk slowly started to clear away, less volatile substances like silica rock and iron started to condense, at first into tiny crystalline dust grains that over time began to be drawn to one another due to gravity and other forces, forming clumps of matter of up to 1 to 2 centimeters in diameter, which over time started to grow at a rate of around 1 centimeter a year, reaching after 1 million years to sizes of up to 1 kilometer wide, being called planetesimals. These planetesimals then began to attract and accrete material from the protoplanetary disk, reaching sizes of up to 1,000 kilometers in diameter in a span of around 100,000 years, and began to dominate their area of space which they orbited. At the end of the planetary formation window, after 10 million years, the disk had fully cleared, leaving behind around 50 up to 100 Moon to Mars-sized objects in this area of space that are called planetary embryos. These planetary embryos, for the next period of time, then started to collide with each other, generating a lot of heat and friction before eventually sticking to each other, and after reaching a certain size, they've managed to become so massive that the heavier elements in them started to sink down to the core as they created their internal layers. At the end of this period of a cosmic battle royale, only a few objects managed to remain, which because of the scarcity of silica and iron in the universe, were limited in how much they could grow. Mercury is a perfect example of this process, which resulted in a failed planet, being very small compared to the other 3 terrestrial planets, as it is mostly a metallic core surrounded by a thick layer of rock, being struck by another embryo in its path as it was forming, tearing the mantle apart and propelling it into its current position around the Sun, being greatly unlucky in its development as opposed to the other 3 rocky planets, that managed instead, through these collisions, to grow enough as to develop their internal structures of layers, facilitating the appearance of their magnetic fields and geological activities, 2 very important factors that made them able to create and retain an atmosphere. This, however, is how the terrestrial planets form. But what about the rest of the planets in the solar system? What about the giants, that are found way beyond the orbit of Mars, having much more dynamic and interesting characteristics? What is their story? To understand how the gas giants formed, and how gas giants usually form, we must first take a look at how a star system is structured. Using as an example our own star system, the solar system, we can see that as we move further away from the Sun, depending on the star's brightness, in our case beyond the demarcation line of 5 astronomical units, the temperatures start to further drop, so much so that volatiles and ices begin to condense. This distance, as I said before, depending on the particularities of each individual star, is a demarcation line in a star system, after which water and other substances start to freeze. And in our case, after 1 million years in the T-Tauri stage, the condensed volatile ices in this area started to grow so quickly that they reached in a short period of time dozens of times the sizes of the rocky planets. And because the protoplanetary disk is mostly made out of hydrogen and helium, when these giant snowballs became heavy enough, they started to attract and accrete this hydrogen and helium, forming a thick atmosphere around the icy cores that grew larger and heavier, eventually becoming dense balls of liquefied compressed gas, aka the gas giants. After a few million years, Jupiter appears, and because the vaporized volatiles ejected from the inner solar system condensed and led to a rapid accumulation of water vapor near the border of the snow line, where Jupiter appeared, allowed for the creation of a circumstellar region of low pressure that makes particles in that area orbit faster, keeping them from falling towards the Sun, creating a literal astral border in space that allows for the faster accumulation of dust and ice, wherein the early life of the solar system permitted the appearance of a planetary core that was 10 times the mass of the Earth, leaving it to attract from early on a lot of hydrogen and helium from its vicinity. Simply put, because on the one side is hotter and on the other side is cooler, a pressure point appears, keeping more stuff on the icy side. After 100,000 years of gas accumulation, Jupiter now has a weight of 150 Earths, and after 3 million years from the inception of the solar system, Jupiter is now fully formed. Due to the fact that it had access to all the matter in the disk first, it managed to accrete a lot of material from it, and after it gained a certain amount of mass, it started to slowly migrate inwards towards the solar system, clearing along the way an even more broader area of the protoplanetary disk, which resulted it to have at the present moment 317 times the mass of Earth, or in other words, having 2.5 times more mass than all the planets in the solar system combined. Shortly after the formation of Jupiter, Saturn formed, having a similar size to Jupiter, but with a lot less mass due to the latter eating most of the material, with the same principle also applying to the two ice giants, Uranus and Neptune, both much more smaller than Jupiter and Saturn, being catalogued as failed gas giants, but nevertheless still having dozens of times the mass of Earth, each forming in a different position in the solar system from where they are located now, forming much more later in the planetary formation window. At the end of the T-Tauri stage, after 10 million years, the disk either was accreted or vaporized or scattered by the sun's radiation and emissions. It took another 50 million years for the sun to enter in its main sequence phase, and another further 50 for the terrestrial planets to finish their collisions. After 500 to 600 million years after the gas giants formed, Jupiter and Saturn fell into a 2-to-1 orbital resonance with 2 Jupiter orbits for every Saturn one. This started to work like a gravitational slingshot in the solar system, kicking Uranus and Neptune in the position of the early Kuiper belt at 50 to 20 astronomical units away from the Sun, disturbing the scattered disk and Oort cloud, which back then stood at the present Kuiper belt's position of 55 to 100 astronomical units, as compared to 600 astronomical units up to 1 light year away for the Oort cloud as they stand today, where light takes 18 months to reach the outermost regions and edge of the solar system, being far beyond the heliosphere, which lies at 50 astronomical units and protects us from interstellar radiation. Neptune's departure to the solar system's edge also disturbed the asteroid belt, that lies at a distance of within 2 to 4 astronomical units away from the Sun, having back then 3 times the mass of the Earth, and now being only a fraction of a percent due to this event, with asteroids being sent all over the inner solar system towards the rocky planets in a period of the solar system's life known as the heavy bombardment. As this chaos took over, icy planetesimals from the outer edges of the solar system were also arriving in the inner system in the form of comets, bombarding the terrestrial planets and instantly vaporizing on impact, with the early atmosphere of these chunks of rocks retaining most of the water vapor released from the comets, allowing the surfaces to gradually cool down as water vapor condensed and started to fall as rain for thousands of years, creating rivers of oceans of water. Venus, Earth and Mars all possessing oceans at some point in their life, with Mars showing signs of erosion and oceans, while Venus had a shallow surface ocean for around 2 billion years. But because Mars is so small, its core cooled faster, putting an end to its magnetic field and geological activities very early in its life, leaving the sun's radiation to sweep away the atmosphere, exposing the oceans in the process as they evaporated, being habitable for only around 200 million years. But Venus maintained its oceans for 2 billion years. Because of its size, being more larger, the interior remains active to this very day. In the case of Venus, though, a different story happened to it. Because the sun increases in luminosity over time, the temperatures gradually increase, causing the oceans to evaporate, which led to a buildup of water vapor in the atmosphere, generating a runaway greenhouse effect that thickened the atmosphere, producing the hottest temperatures that we find in the solar system today, at around 470 degrees Celsius. While out of the 4 rocky planets, Earth was the luckiest, managing to retain its oceans to this very day, permitting us to evolve, deduce, and understand all of these concepts. The solar system is humanity's cosmic backyard, where we can experiment, closely observe, and leisurely explore the surrounding space, as opposed to traveling into intergalactic space, where distances are much more vaster and inaccessible, permitting us to make our baby steps as we prepare for our future of space exploration. Studying it helps us to better understand the universe, our past and the future up closely, allowing us to further increase our chances of survival as we further understand our surroundings. Okay. Thank you all for watching the video. I hope you enjoyed it, and until next time, take care.